Okay, so it's a pleasure to have Smitha Vishveshwara from University of Illinois, Urbana. But as you can see her background, this cannot be Urbana. So she is currently logging in from San Diego, where she is spending her extended sabbatical. So Smitha did her bachelor's and she got magna cum laude from Cornell University in '96, and she did her research with David Mervyn and Carl Frank in undergraduate level. She completed her PhD in theoretical physics from University of California, Santa Barbara under Matthew Fisher, and where she worked on localization in superconductors, Luttinger liquids, quantum entanglement, and all those subjects. And after a postdoctoral tenure with Paul Goldbart and Tony Leggett, she became assistant professor at Illinois in August 2005, where she's a full professor now there, and she has spent a long time there. So Smitha has apart from doing exceptional physics, she has very good outreach insights on how to communicate physics, which I saw in one of the APSs. She was even directing a play on a woman astronomer, and it was pretty impressive that her outreach skills. It's very rare that she has such multi-talented outreach skills where she can communicate physics. So it's a pleasure. She has a lot of family connections to physics also, which I'm sure she's going to mention. And Smitha, it's yours now.
Thank you so much, Sriram, for the invitation, and all of you for being here. And I should say sabbatical is over, but I'm conducting, indeed, as Sriram says, conducting University of Illinois business remote from the San Diego area. As for the physics art thing, indeed, we did host a play, but we also created another piece called Quantum Voyages, if of interest. So coming to you all today now, it really is a pleasure to be here at CCNY. And it's special not only because of the fond friendships and collaborations that have formed across the decades, but in fact, my connection, as Sriram alluded to, goes pre-birth. So my mother in the 1970s, when I was inside her, received her PhD in quantum chemistry at CUNY. And so I, before I was born, I guess, spent a lot of time in the area, exposed to science. And I should say, in some sense, coming full circle, again, I get the feeling that I am with you all, but I can't see you all, but I can feel your presence. So, so that's just a little bit of my connection with CCNY and New York. So very happy to be here today. As for non-equilibrium quantum dynamics from the atomic to the cosmic scales, it's actually something I've been working on with multiple collaborators for a long, long time now. And so just to set the stage, of some of the glimpses that I'll give you today, starting at the beginning, and I really mean all the way at the beginning, with the Big Bang and the inflationary period, which actually I'm a condensed matter theorist, I should specify. There are many of you in the audience who know this story much better, but the point of interest here goes back again to the 1970s when Tom Kibble proposed a scenario for structure formation in the universe, when he said that during the rapid cooling stages, it's possible that the universe went through a stage where it went into a symmetry broken phase. So some kind of ordered phase where the vacuum itself acquired some expectation value. And he gave this as a possible picture for the formation of domains and strings, not in the modern sense, but essentially structure formation of all sorts. And I'll tell you about that in just very briefly. But the main thing here is that you're rapidly cooling from a state of disorder to order. So now, years later, Zurek proposed that this sort of thing perhaps could also be realized on Earth, in systems around us. And in particular, he looked at the case of helium, superfluid helium. And so again, the idea here was to quench or to dynamically tune some parameter through a critical point to go from an ordered phase, from a disordered phase to an ordered phase. And in that, in this scenario, create defects or vortices. So essentially, if you look at, there's a sort of universality in these pictures. It's equally applicable in the cosmic scale or in the mesoscopic scale of some condensed matter system. And the idea here is what you're really looking at is some kind of spontaneous symmetry breaking. And then you can ask, how do I go from disorder to order in time? How does this actually take place? And so the picture that they had in mind, the Kibble-Zurek scenario, is that you form regions of local order in various non-causal regions. These regions grow, and then when they actually come together, they would all like to have some kind of global ordering, but there may be regions in which the order parameter cannot unwind, and you have the formation of a topological defect. So this is the Kibble-Zurek picture. And a lot of what I will be talking about for the first half of this colloquium really has at the back of it this sort of picture. So to tell you what I will speak about today, so in what follows, so first off, let me tell you a little bit more about this Kibble-Zurek scenario in the case of superfluids, superconductors, magnets, condensed matter systems. Then I will tell you a little bit more about how there's a very concrete prediction, and it tells you about the scaling of the defects that you have, defect density. You can see that there's a universal scaling law that depends only on the critical behavior across the transition. And this is the Kibble-Zurek law. I'll tell you a little bit about it. Now, there are three things, there's a couple of things that we've looked at over the years with respect to this kind of Kibble-Zurek scenario. Everything that I showed you right now is actually for some systems that have some kind of local order. So what I'd like to ask at the heart of this colloquium is how does this picture remain, or how does it change when you're looking at topological systems that, as you all know, have surged into the limelight in the past decade. So one of the differences, one of the key aspects is looking at ground state degeneracies and the like. So we'll be looking at quantum quenches. But another really fascinating aspect is that when you're looking at defects in superfluids, for example, these are typically vortices. When you're looking at defects and excitations in topological systems, these can be fractional in nature. They can be anyons. And again, when I get to the anyons, I'll mention some beautiful new developments that have taken place in the field very recently. And I will be discussing this in the context of the quantum Hall system. And finally, what I would like to show you in a very, very simple system, looking at the dynamics of these fractional particles, I'd also like to show you that the same quantum Hall system actually has parallels to black hole physics. And I really hope to get there, get to that last, to have enough time to discuss that in detail. So what I would like to tell you is that specifically, there are parallels between the Hawking-Unruh effect and what are called quasi-normal modes, which are related to the ring down, for example, that you see in these gravitational wave detectors. I would like to argue that this sort of black hole physics has its parallels in the quantum Hall system. So that's sort of the roadmap for where I will be going. And Sriram mentioned also, well, so first off, when Sriram and I were trying to figure out the topic, this was weeks ago, but obviously for this last point here, talking about black holes, last week was tremendously exciting for the announcement of the Nobel, for Penrose's legendary work on black holes and the fundamentals of black holes, and then Genzel and Gez's work on discovering the supermassive compact object at the center of our galaxy. So it would be a huge omission on my part if I didn't sort of take a moment to celebrate this. Now, Sriram also mentioned my sort of parental science connections. And so just to tell you, and I told you a little bit about the 1970s, during the period when I was being born in 74, close connections to New York City. And at the same time, my father, a late black hole physicist, general relativist, was forming actually a very close connection with these two gentlemen here, Roger Penrose, who you just saw, and John Stachel is actually another general relativist and Einstein, an editor of Einstein's letters. So this was a picture that my father took in our home in India, but in fact, the formative years for their friendship and Roger Penrose heavily influenced my father's work. My father in the 70s had worked on stability and geometry of black holes and then predicted quasi-normal modes. So it's also on a personal note, we're very, very joyful that his friend has this, is being honored with this, and the other two fine scientists as well. So I should just say that at the end of my talk, I hope to come full circle. And I should say that a lot of this was taking place in New York. So even though I'm a condensed matter physicist, black holes and the cosmos have been my first love. And so I really hope to show you how I can bring this back full circle in the quantum Hall setting. Okay, so now let's actually get to the heart of this quench dynamics and the Kibble-Zurek scenario that I told you about. So first off, I mentioned the cosmos, the context in the cosmos, which I won't go into in detail. I will focus for this part of the talk on the things that I am much more familiar with, namely superfluids and the like. Okay. So we have a variety of candidates that can show this kind of really beautiful scaling behavior, dynamic scaling behavior, and the Kibble-Zurek scenario. So just to name a few, Helium-4, for example, where it was first discussed, that's a fine system where you can actually there are many different phases, particularly the helium, the normal liquid and the superfluid. Helium-3 is known to have a very unique pairing symmetry. That's yet another place where you can see this kind of dynamics, not universal dynamics come about. And of course, superconductors. So particularly if you're looking at BCS paired, for example, that's another place where, and in fact, even high TCs, in fact, the actual pairing mechanism doesn't matter at all. All that matters is that we are looking at a scenario where we go from an disordered to an ordered phase. So now, all these systems are characterized by an order parameter. In this case, it happens to be a macroscopic wave function that is shared by the entire system. And so now if you're looking at spontaneous symmetry breaking, what you're really talking about is that the order parameter has a magnitude and it has a phase, and the spontaneous symmetry breaking happens in, so this is a U1 symmetry that gets broken, so a particular phase gets picked. Okay, So that's for the order parameter. And now when we're looking at defects in the system, what you can have, these topological defects, the typical ones are vortices, for example, where the order parameter can wind around by 2 pi, for example, or maybe 4 pi, anything such that it comes back to itself and is single valued. So that's a place where you have a topological defect and the system can't unwind out. These have been imaged, for example, in cold atomic systems really beautifully, and also superconductors, bitter patterns, for example. So these are the possible defects that you might have. Okay, and so now we're looking at superfluids, but we could, as I told you, this is a scenario that's absolutely universal for any kind of local ordering. And so I can think of the same picture in magnetic systems, where, for example, I could have a Heisenberg magnet or an XY ferromagnet, for example. And here, as a possible picture you could have, this is really showing you dynamically over time how you have these ordered regions coming about, and finally trying to find some global order, but in the process topologically being prevented and having to have some kind of defect. So the defect could be a domain wall, for example, or it could be a point-like defect. The transverse Ising chain gives you a very, very simple example where you can both, in terms of theory, there's a lot of analytic progress that can be done, and experimentally, the latest experiments are really looking at, for example, cobalt chains and the like to test this kind of quench physics. Okay, so just to go over the scenario, the picture to have in mind is that you have, I already told you about this, I have these local regions of order coming about. They haven't talked to each other, they grow and grow and grow when you do a quench. So when you quench in time from a disordered phase into an ordered phase, and you could be quenching at some rate, and this doesn't have to be temperature. In fact, most of what I'll be talking about is quantum quenches, where you may tune a parameter of the system like the magnetic field. So you have these regions of order coming about, and then this kind of giraffe kind of pattern comes about. And you can see, for example, this is an example of U1 symmetry breaking. And you can see that when these three regions come about, they can't really unwind out of each other. So at that point, you have the formation of a topological defect, a vortex, for example, in a superconductor. Okay, so that's a scenario. And of course, depending on the symmetry, depending on the features of the order parameter, the dimensionality, you can have defects of all sorts. Vortices, maybe the structure formation we talked about right at the beginning. Jack here blowing these cigar rings, which actually, in fact, have more or less the same structure as vortex loops in a superconductor. You could have skyrmions, hedgehogs, crystalline defects, all kinds of different things emerging. And a little bit later, I will show you some experiments that have been done to explore this kind of scenario. One of the reasons that I really love this physics is the universality. So any system that might have any kind of interesting defect structure, one possible way, of course, an experiment, in reality, it's really hard to probe, but the point is, anytime you are able to go from a disordered phase into an ordered phase, this sort of Kibble-Zurek physics must hold, and it's one way of generating interesting defects. Okay, so let me now do something a little more concrete. Let me tell you the precise statement that came about through this Kibble-Zurek analysis, namely the prediction of universal scaling. So while I do so, Sriram, is it typical to take questions midway through?
We will stop you on the way.
Okay, okay,
Yeah,
yes.
but let me ask, if are there any questions at this point? Yeah, so what I will do is that people will text me in the chat and there will be some queue and then I will let them at you one by one.
Okay, perfect.
Yeah.
So, so what I'll do is now I'll go through the Kibble-Zurek scenario, give you a little idea of how the scaling comes about. And then after that, I will shift over to topological systems. So maybe at the end of that, I would be a good time for questions. Okay, so now there's a very concrete prediction made by Kibble and Zurek, which is once you've done the quenching, as I showed you, you accrue defects. Now, if I were doing the quenching at some rate tau, so some characteristic timescales tau, so a rate tau inverse, then there's a very concrete prediction. The prediction says that the defect density does not depend on the microscopic details of the system, just like critical phenomena. All it depends on is the tuning rate, and it obeys a power law. So the faster you tune, the more defects, as you might imagine, but there's a universal power law scaling that only depends, the exponent only depends on the dimensionality of the system, the correlation length exponent, critical exponent, the dynamic exponent, and that's it. So what I will do now is I'll give you a flavor for how you can think about this.
So I have a question here. So
yes.
at this point, you're just tuning through like a classical phase transitions, right?
Oh, sorry. Yes, thank you. First off, it has to be a continuous phase transition.
Right.
And now I will say that this applies both for classical or quantum. So this kind of thing goes through for either of them. The arguments for the two and the analysis are a little different, but the argument that I will give you here now is general to both.
Mm-hmm.
Okay.
And the quench rate that you are talking about is like, so I just want to intuitively understand what is the criticality associated with that rate. So you're just tuning across a transition point. So in a dynamical sense, what is being changed from one side to another?
Okay, so I'll tell you more about that, but maybe, for example, let's just take paramagnet to ferromagnet transition. So just so we, as an example. So maybe at some value H, the magnetic field, you're in the paramagnetic phase, and then let's say that you do a linear quench. So you change the magnetic field linearly in time at that rate tau, right? And I'll show you the explicit example. Then what you can actually show is that, and I'll tell you what, I'll give you the arguments in just a second.
Yeah, sure. Yeah.
You can see if that makes sense.
Yeah. So actually there is one more question. Alex, go ahead.
Let's say, so if let's say I have a tight binding system, then there's some kind of hopping strength. So definitely you don't want that time scale to be comparable to these sort of microscopic things that are there. So what we're assuming is that the rate at which you're tuning, I will show you it's fast no matter what. I'll tell you in a second as to why. But then you're assuming that you're well within sort of the high energy cutoff of the system. Okay.
Thank you.
Sure. Yeah. So so now, as with any phase transition, you know that you have a diverging correlation length scale that diverges as a power law, and this is the correlation length exponent. And this is the power of universality, that you don't care about the microscopic details. So for example, I could look at the cosmos scenario, I could look at superconductors. If the symmetry being broken is U1 and you're in the same dimension, you'll be predicting the same kind of physics, which is pretty spectacular actually. So then along with that, I will not show this video. Okay, I will show this video at the end if anyone's interested. There's some beautiful dynamics with superconductors, that there's a superconductor there, and it's there's a magnet hovering over it, and you can actually see some really interesting dynamics, and you can see something that I think is critical behavior. We have to investigate that further. But the main point is that as you get close to the critical point, you also have the relaxational timescale of the system also diverges as a power law, okay? And if you have a gap closing, for example, it's related to the inverse gap. It is the inverse gap for quantum phase transitions. So this Z here tells you the rate, tells you the manner in which the relaxational time also diverges. So as you get closer and closer to the critical point, it's harder and harder for the system to relax. So now look at the Kibble-Zurek. So what I'm plotting here is I have this diverging relaxational time scale. And now imagine I do, like I was telling Sriram, I do this linear quench. So let's say that I'm changing the magnetic field, and now I just care about the magnitude of the field. So imagine that I'm changing this, let's say, magnetic field linearly in time. So it has a T over tau. Tau is my quench rate. Now, no matter how small tau may be, the fact that you have a diverging relaxational time scale close to the critical point means that no matter how slow, whatever the value tau may be, you will absolutely fall out of equilibrium close to the critical point because the system cannot catch up. It's the relaxational time scale is diverging. So when you compare the characteristic quench rate to the diverging relaxational time scale, when these two become equal, then beyond that point within the critical regime, the system cannot equilibrate. That is the non-equilibrium region, and that is the point at which you have all these defects accruing, okay? And that's why you kind of see the universality. So let me just, so now to look at where you get this universality, so essentially what you have is there's a relationship. So now you have a relationship for when you fall out of equilibrium. And so then that gives you a relation between the characteristic quench rate and the characteristic features of your critical system. And so then you can show through a simple argument that, for example, let's say you get the, let's say you're interested in the density of defects. Then, for example, you can use this relationship for when you fall out of equilibrium to show this sort of Kibble-Zurek scaling that I told you about. This is simple scaling behavior, and this is at the heart of what Kibble and Zurek predicted. And so let me just pause and say, this is the scaling, and what I showed you right now is just through simple scaling arguments, you can derive the Kibble-Zurek scaling behavior. Now, for example, if you're to be looking at the transverse Ising chain, I don't have time to go into it, but it's a very lovely, beautiful calculation. You can, sorry, this is the transverse Ising, for example. Actually, this one in particular, you can solve exactly using, if any of you have dealt with these Jordan-Wigner strings. Actually, I know many of you have. You can do this transformation, and in theory, you can actually derive the scaling law analytically. Okay, it's a very simple and elegant derivation. And
I have one technical question here. So can you do something like a Keldysh RG to see all this? Do people do that?
Yes, actually, okay, so again, it really depends on whether you have thermal or quantum. In fact, the quantum ends up being much easier. And absolutely, for example, if you wanted to do finite temperature, you'd have to do something like Martin-Segier-Rose formulation. So it would be, yes, so the answer is, in general, you would definitely need to do Keldysh to handle the non-equilibrium aspect. And then to get out scaling, there is a sort of dynamic RG that you can enhance this with and get a lot of this out. So good question.
Okay.
Okay. Only in some cases though, not all cases. And in fact, if you want, we can chat later. There's some really open, really interesting open problems on that. Okay. So I should just mention there's a few other measures that you have. There's the net excitation, so it doesn't have to be defects, it could be spin waves, it could be anything. If we're looking at quantum systems, you can also have other measures. So for example, if you do the evolution of the quench, then in the final state, what is the extra energy compared to the ground state energy? So that's the residual energy. You can look at entanglement properties. Adiabatic fidelity just means the time evolved ground state, the time evolved state, how does it compare to the local ground state? So these are all measures that can be used. And let me just say that these experiments, for various reasons, are hard, and they have been performed beautifully in actually helium-3, in cold atomic lattices, optical lattice systems. So that's looking at superfluid to MOT or MOT to superfluid. And then there's all kinds of other systems, even in superconducting rings. And then I'm actually collaborating with various groups to see if these can also be done in magnetic systems, particularly with Tom Rosenbaum. We've been having this discussion for a while. And for example, his is one of the real leaders in being able to quench and dynamically tune magnetic systems. Okay, so that's as far as the Kibble-Zurek goes. And now let me talk about how this whole quench dynamics plays out in topological systems, okay? And so now, what are topological systems? So first off, a lot of the picture that I gave you hinged on there being some local order and some defect being created. And by the way, this is collaborative work with many, many people. Deeptiman Sen's been my long-standing collaborator on many projects. And Wade and Suraj used to be my students. Vasudha was a postdoc in Urbana. And then Graham and Eust were both collaborators in Ireland. So this is work that we did with them. So now, coming back, topological materials. How would I like to, what are the features? First off, there's no local order. Now they're characterized by global invariants. So these could be Chern numbers, for example, related to, if you're looking at quantum Hall, it's related to the Hall conductivity. Well, okay, you can have Hall conductivity, you can have Chern numbers. And then the other kinds of measures are ground state degeneracies. So again, quantum Hall system, if you're looking at the fractional quantum Hall system, if you put the system on a torus, you can see that the ground state is degenerate. Entanglement, then the presence of these surface states is also very typical. And then finally, what I'll discuss at the end are fractional excitations. Okay, so first let's talk about ground state degeneracy. And I think this part I will kind of go through a little faster just because I want to show you the anyons as well and the black hole. So here what you have is, as an example, there are these Majorana wires, which are P-wave superconductors effectively. And you have the topological order really comes, you can see it in the presence of these sort of bound states at the end. This one here is a spin system, the Kitaev honeycomb. And in that one, you have no local order whatsoever. But then, for example, you can have, again, topological ground state degeneracies and the like. It's a really paradigm topological system. So now, if we were to do the same quenching procedure, let's say in these two examples, specifically what I will tell you is that we'll first look at ground state degeneracies, then we'll look at the other things such as particularly anyons and fractional excitations. Okay, so now here's the situation. Specifically, what I will tell you is that the ground state degeneracy makes a huge difference to this whole Kibble-Zurek scenario. So in particular, if I were going from a system that had, if I were going from a topological phase that had higher ground state degeneracy to one that had lower, then you can see that there's something very drastic going on with the quenching behavior that you don't see in these systems with local order, okay? So in particular, what I will tell you is consider this system or this scenario. Exactly as I said, I go from higher degeneracy. So for example, in this Majorana wire that I told you about, in the topological phase, you have a degeneracy of 2. And then in the trivial phase, you have no degeneracy at all. And these degenerate states, the ground states, are actually characterized by some kind of invariant. So for example, for the Majorana wire, it's the number of fermions that you have in the system. So there's an odd or even. So it's the parity of the system that, that identifies the degeneracy. So one of the ground states has odd parity, the other one has even parity, and that's an example. In the Kitaev honeycomb, for example, you have a degeneracy of 4 in one phase and a degeneracy of 3 in another phase. So now let's go back to the quench. Imagine you're quenching from higher degeneracy, and these are all topologically robust numbers, so they're invariants. So if you look at this phase 1, for example, and you look at, let's say, the green that I have here, this ground state has no partner in the final phase. So what happens to it? What happens is that the overlap between this green, and if I were to time evolve, and the final ground state is 0. So as a result, what you end up getting is that there's a mismatch that actually forces, unlike the Kibble-Zurek scenario where you had some excitations, some defects, what you end up having here is that you have the entire weight going into the excitation spectrum. So if you pick the wrong state, such that the wrong ground state, such that it has no overlap in the final ground state, then as opposed to just having some defects that follow scaling behavior, everything goes into the excitation spectrum.
So does the gap closes and reopens at the critical point while doing that?
Yes, yes, thank you, Sriram. So that's a really important point. Otherwise, you won't be able to do this. So, so you really have this gap that closes, and then you can actually see that, in fact, for most of the transition that you have, you can have a Landau-Zener type transition, but really it's the gap closing that actually takes you, what is originally the ground state, you can actually see it going off straight into the spectrum. So the gap closing is extremely important.
And so I have a follow-up regarding that. So I can envision similar kind of things in integer quantum Hall plateau transitions, right?
Yes.
So,
yes.
So that is also accompanied with gap closing, and also what changes is the churn number definitely changes, and also the number of edge modes is the only characteristic that changes across the.
Yeah, that's a great point. And by the way, I think I'm going to answer this. And yeah, so this is a really good point. Thank you also for asking me. It turns out this thing that I told you, right, that it's impossible to go back to the ground state. You're absolutely right. It also happens for the integer quantum Hall system. And so it's a little problematic because there is sort of, if you're looking at the churn number, so just let's take some kind of system where, how shall we do this? Okay, forget the gallium arsenide. Let's take some of the quantum anomalous Hall or one of these things. You can see that, for example, there's a spinner. It's because you're just looking at some kind of bipartite system. You can see that the churn number you can get in some kind of block sphere. You know what I'm saying, right? Mm-hmm. Yeah. So one of the things you can show is that no matter what you do with the quench, the crucial sort of vector that defines the Chern number for you refuses to flip, okay? And so you can say, this is a real problem. We all know that we can actually obtain different quantum Hall states, right? We're dynamically tuning this. We're changing the magnetic field. We're changing whatever it is. So it turns out that really, and this is something very new that's come up, and it's work that, in fact, during my sabbatical in San Diego with Dan Aravas, Yizhuang Yu, and Wei Ting Kuo, who's a student of Dan, we've been looking at how we can actually go from one topological phase to another. How can we get to the ground state? And the answer to that is that it turns out that you cannot do it unless you actually have dissipation. So along with this, what you really need to do is either you have to couple it to an environment, to a bath, or what you have to do is you have to effectively have a system where you have weak measurement, for example. If you observe the system, that's one way of tipping the spin to get the right Chern number, it turns out. So it's a great question, and it's a hard problem. But we're getting answers. In fact, you get some really lovely scaling behavior also for when you get into the dissipative realm as well. Okay, so what I'll do is, because I have not a lot of time left, by the way, the adiabatic theorem that says that you're always tracking the ground state, which clearly is not the case, I've put violated in quotes because it's exactly as Sriram pointed out, the gap is closing. So you really, strictly speaking, are no longer adiabatic. But this is a phenomenon that we like to call topological blocking. It's really coming from the ground state degeneracies. Was there another question?
Yeah, Alex, go ahead.
I was just wondering, this proliferation of the defects don't lead to dissipation in some sense as you're quenching?
Okay, good. So actually the proliferation of defects in and of themselves is very subtle because, or rather very complex. In fact, what we really need to look at is different time scales. So what I told you close to the critical point always holds. When you go far from the critical point, however, what happens is not only dissipation, because you do have excitations. And one way to look at it is, if you're quenching, you're putting energy into the system. And where did that go? So you find that post-quench, one thing to mention is the defects and the dissipation, all that comes into play. Another thing that can happen is that the defects can annihilate each other, like if you have a vortex and an anti-vortex. So great question. There's a whole other regime where all this comes into play. Okay, so let me just skip. I was going to talk about surface states, but in the interest of time, let me just skip ahead. I will tell you that surface states also play a role. But Sriram, is it okay if I fast forward to anyons? Because I'm kind of excited about those. I'll take that as a yes. Okay, so let's not go through this. Okay. So let me tell you that when you're looking at the edges and the like, there's also some very, very interesting dynamics. But now let's look at the thing that I know and love, and I've been working on for maybe almost 20 years now. So, and that's fractional excitations. So now, and I also want to tell you, because there's been incredible progress in the last few months on this actually. So one of the things that you have in the quantum Hall system is that particles, quasi-particle excitations are anyons. So specifically, they have fractional charge that doesn't make them an anyon. So for example, if you look at Laughlin states, then you can have, first off, I should say these are effective emergent quasi-particles. They're not fundamental particles. But for example, you can have things with fractional charge, E/3, E/5, and the like. There have been some really across the years, there have been, okay, so there have been some marvelous ways of fractional charge has actually been measured in short noise experiments. We'll talk a little bit about those. Now, they also have fractional statistics. They're not fermions or bosons. These typically end up being anyons, which means under exchange, they can pick up a phase, a fractional phase, not +1 or -1, some sort of phase factor. So now, of course, you can ask about what sort of quasi-particles emerge in this scenario. So for example, now it doesn't have to be ordered states. It could just, rather locally ordered states. You could have, for example, Sriram had in the back of his mind, tuning between different quantum Hall states. So it turns out that, of course, you can have the emergence of these kinds of anyons through quenches. And ultimately, that's the sort of physics that we want to be looking at. But even understanding two anyons turns out to be quite a challenge. And so that's really kind of what I'd like to talk about in the next 10 minutes that I have, and also bring it back to black hole physics. I should mention—
you have more time than that. We started a bit late, so you have like 15.
Do I have 15 minutes?
Yes, you have.
Yes, okay, good, okay. Because I don't want to shortchange the black holes. I think I can do this in 15 minutes. Okay, so just by the way, people have been, the hunt for anyons has been on for, over a decade, actually much more than that, 2 decades. So, and I'll just mention that Moti Heidblum last week was really the week for all kinds of recognitions. And he'd done some spectacular work in this realm. Even though anyons hadn't been detected, there were these marvelous, he's been working on short noise, showing fractional charge. He's looked at quantum statistics of electrons in interferometers. And so the Buckley went to him last week. The other thing that happened, let me see. Yeah, the other thing that happened in the last few months was that there were 2 experiments that actually showed evidence for anyons. One was in a beam splitter setup, and the other one was in an interferometer. So now let me go back and tell you a little bit about what we've been doing for a long time, actually. And I should say the beam splitter, both these experiments, I'm a theorist, both these experiments were incredibly exciting because they really nailed down what the community had been predicting for a long time. And the beam splitter is something that I looked at in more detail. So it was just incredible to see evidence of these anyons. So what I'm going to tell you is I will tell you a simpler setup of 2 anyons, quantum Hall anyons. And I will go through, this will not be complicated. There's just a tiny little bit of technicality that I'll have to introduce to you. And I will show you how these anyons, what the dynamics is. And in particular, when you put them in saddle potentials, you can ask so if you have, as I show you here, 2 particles in a saddle potential, of course, it's created by electric and magnetic fields, for example. It's not a physical saddle like so, but you can ask if they come down from the opposite sides of the saddle, will they bunch like bosons or light, for example, and both go along this path, or will they anti-bunch and go off in opposite directions? So that's kind of where I want to go in the next few minutes that I have. Okay, so this is the only technical part that I have. We are looking at, if we're looking at quantum Hall anyons, there's a beautiful, there's actually a very beautiful description of just 2 anyons. Alex, if I may ask, were you at Lesuche in 1998?
Me?
Yes.
No.
No, okay.
No.
Sorry, pardon me. That in 1998 is where I learned all this. There was a Lesuche lecture series, and that was a long time ago. So let's see this here. So forgive me if I was a student back then, and then we had this really a nice lecture on this sort of lowest Landau level physics. And one of the things you can show is that you can actually look at two particles in a magnetic field, go into the lowest Landau level, and the way you can treat them as anyons is that you can go to their center of mass and relative coordinates, and you can actually show how you can get out the phase factor. So just briefly, when I look at the anionic feature right here, in the center of mass, when I take x1 to x2, so I kind of, or r1 and r2 when I do the exchange, what I'm really doing is when I look at the relative coordinate, I'm taking r2 minus r. And so really what I have here is when I take r2 minus r, I gain this fractional phase, and that's really where I have the anionic statistics coming into play. Okay, so now, and then there's a very lovely algebra. I am unable to advance my slide.
Is it an artifact of non-commutativity in principle?
So non-commutativity is extremely important. This particular feature, no. This particular feature, no. But what I will do is you can actually, so one of the things you can do for these anyons, the non-commutative aspect comes in creating localized excitations. Okay.
I just want to clarify this. So for myself, so you are imposing this as a condition on the wave function, right? To make it anionic.
Yes.
You're putting it by hand, this alpha, and then.
That's right.
Okay.
Yeah. Now, you mentioned non-commutativity. Let me just say a little bit about that. Where you find the non-commutative thing is that you can never have completely localized localized anyons. X and Y don't commute in the lowest Landau level. So there's a sort of spread, okay? So there's a tiny spread. And so what you really need to do is create coherent states, okay? So I'm not going to go over all the details of these coherent states, but I will tell you that to create localized anyons, what you can do is you can give this sort of boundary condition, and then you can create coherent states that respect the boundary condition. So those of you that are used to coherent states in optics or lowest Landau level physics, it's the same thing. The only thing is you have to have fractional angular momentum because of this anionic boundary condition. Okay, so now what you can do is you can say, what happens when I put two of these anyons in a saddle potential? So if I look in the XY plane, for example, what I've drawn here for you is a saddle potential given by this equation. And actually in all these quantum Hall experiments, this is what you have. You have these point contacts, and in the bulk, you actually have quantum Hall, you have a saddle potential. This, like I told you, acts very similar to a beam splitter, because these coherent states, what they do is they can come from two sides, and then they either go off into this upper branch or this lower branch. Okay, so it's like a beam splitter. So now you can ask yourself, this is where the anionic statistics comes in. You say, these particles, when they come along, do they both go in the same direction, or do they go off in opposite directions, okay? So I won't go into all the details of this, but let me just say, and I can go over the details for any of you. I know that people do want to leave, so I'll make the connection to the black holes. So one of the things that happens is that you actually have, if you look at the whole thing, if these were bosons, they both want to go off in this branch here, or this branch, it doesn't matter. If these were fermions, you'd want one going up and one going down, anti-bunching. So let me just tell you that it ends up being that, never mind all these details, anyons are of a sort of split nature. Depending on their initial separation, it turns out that some of the time they may want to act as bosons, and some of the time they may want to act as fermions. So this is, so now coming back, when I look at two anyons and I look at the dynamics, and it is again quench dynamics, because what am I doing? I'm keeping them in the lowest Landau level, I'm turning on a saddle potential, and when I look at the dynamics, I find that in some situations they act like bosons, in some they act like anyons. Okay, so I will take a small pause just to sort of make that, statement. And now let me go on to the final part. How much do I have? 5 minutes?
5 to 10 minutes, don't worry. Yeah.
Okay, thank you. Okay, so I don't, yes, fine. So here is the finale now. Okay, these are trajectories in the lowest Landau level. And as I told you, they could be realized, for example, in this quantum point contact geometry, where essentially you have a Hall system, and then you're pinching this very, very, very close to such that usually you have these edges going around and they come really close to each other, and then you can have tunneling of these quasi-particles. That's a quantum event, okay? So one of the things that you can see now is, if you were just to look at classical trajectories, no tunneling whatsoever, look at where this particle is going. It cannot go out to the other side if it were a classical particle. And this is really how the quantum Hall system behaves if there were no tunneling involved. So if you look at these trajectories, everything that's on this side at the bottom stays on the bottom. Everything that's on top stays at the top. So in some sense, this is really like a horizon. And what I will tell you in the last few minutes, like an event horizon in a black hole. What I will tell you in the last few minutes is that it's much more than that. It turns out that there's a very profound mapping between the event horizon kind of picture that I give you here and what you find in general relativity and in black hole physics. Okay, so that's just the very last part, and it's work that I've been doing with my two students here, Varsha and Suraj, and Barry, my collaborator, Mike Stone as well. And my father, when he was alive, taught me a lot of the basics of some of what you see here with the black hole aspect. And so this was something that we dedicated to him, work that we dedicated. So first off, let me just say that the analog turns out to be quite solid. This is work that Mike Stone did, where he showed that I told you that we're talking about tunneling across the saddle, right? And now it turns out that there's an exact mapping between the tunneling, quantum tunneling, that you have here in the quantum Hall case and the Hawking-Unruh effect. What is the Hawking-Unruh effect? It's looking at the way, for example, Hawking looked at it in the situation where you have black hole evaporation. And the idea here was really to look at evaporation in terms of this sort of quantum tunneling. Specifically, the treatment was to compare an inertial observer at very far out infinity to an accelerating observer. And if you have any sort of vacuum, for example, you can compare the vacuum between these two frames, and you can actually show that what's the vacuum in one frame translates to excitations in another frame, and that's really the sort of evaporation that you have, these excitations. They're Bogolubov type excitations. So it turns out that when you look at this problem, and you look at not any particles at all tunneling across the saddle potential, this tunneling parameter is exactly what you would, it's exactly the same as what you would have for the Hawking-Unruh effect. Maybe I have only two more statements with regards to what we did further in this. So let me just make those, and then it's more or less towards the end. So I can just take questions after that. So now this is one aspect of black holes. There's lots and lots of other aspects. And in some sense, if we go back and come a complete circle, we all, of course, have been celebrating the detection of black hole mergers ever since the LIGO announcement in 2016. And then we've had so much else come out in LIGO, Indigo, Virgo, all kinds of amazing detections. And in some sense, this is sort of the most non-equilibrium thing that you can be looking at, the merger of black holes. Now, one of the things that actually comes out, a signature related to the ring down, is this sort of, oh, sorry, as an aside, I should say that there's a lot of analogs between black holes and condensed matter systems that are being explored. But coming back, one of the things that you really have is this ring down, quasi-normal mode. And that is the characteristic signature of a black hole. So in some sense, if you wanted to explore this, one thing that you could do is to really look at a wave packet, scatter a wave packet off a black hole, see what comes out, look at its temporal behavior. And now if it's a Schwarzschild black hole, meaning it's spherically symmetric, it's only characterized by mass, then you can see that the decay depends purely on the mass, okay? And so this is what I did learn through my father in his 1970 work in New York City, close to where you all are, at least where CCNY is located. And so since then, there's of course been lots and lots of different approaches to looking at quasi-normal modes. What we found was that once we had the parallel with the Hawking-Unruh effect, now the next thing to do is it's exactly the same setup in the quantum hall to look at these quasi-normal modes. So the Hawking-Unruh effect was just sort of looking at tunneling amplitudes across this point contact or across the saddle potential. Now what you can do is you can say, what happens if I just scatter a wave packet and look at what happens dynamically? And it turns out that there's a complete one-to-one correspondence between these two problems. So here you have wave packets scattering off of this black hole metric. And then here you have tunneling across the saddle potential. And by the way, Sriram, again, the X and Y not commuting, you can actually convert it to a quantum one-dimensional problem. And so the thing that unifies these two problems is that they both follow the physics of scattering off an inverted simple harmonic oscillator. So there's a very beautiful correspondence, both from the black hole side and from the quantum Hall side. And so in fact, these quasi-normal modes are something that were predicted in the black hole scenario, and they should also exist in quantum Hall point contact geometries. So it's actually an open problem yet to be discovered. Okay, yes, yet to be measured, I should say. It exists, it's something that can be measured. Okay, so that brings me to the end of my talk. Let me just recapitulate. We've looked at quench dynamics in many different scenarios. Hopefully I've given you a glimpse of how this is a very, very rich arena. And so we looked at Kibble-Zurek scaling as an introduction, what happens in topological systems, and then what this sort of turning on some kind of potential may do in the case of quantum Hall systems, particularly with anyons. And then finally, how there's a parallel, there's a black hole parallel in quantum Hall systems, giving you this sort of dynamic quasi-normal mode. So with that, I will end. Thank you for being patient, and thank you all for being here.
Yeah. Thanks, Smitha, for a wonderful talk. Are there any questions? I have few, but I will wait for others to ask and then. So let me ask my questions then. So I was wondering, what is in this analogy, can I just think of a electron, some kind of a Fermi liquid, and then think of the same analogy? Because I didn't understand if there is a role of topology in this analogy in any way.
In which aspect?
So for example, you were looking at anion scattering of each other through around the saddle potential. Let's say we take two fermions or two bosons scattering of each other.
Yeah.
So then there will be some so I think maybe my question is that in Michael Stone's paper, with Hawking and radiation analogy in quantum Hall effect, let's say if I, instead of quantum Hall effect, I just take a electron liquid, which is non-topological. So will there be still any analogy? So what is the role of topology in the system?
Yeah. So I would say not so, in this case, not so much for that second part, not so much topology as lowest Landau level physics. So you really needed that thing where X and Y don't commute.
Oh, I see.
And then what happens, so essentially think of it this way. The saddle potential is, okay, let's take, instead of X times Y, you can imagine a saddle that goes as X squared minus Y squared. Okay. So now if Y is conjugate to X, it's playing the role of momentum, right?
Yeah.
So instead of X squared minus Y squared, let's just do Y squared minus X squared, okay? So let's do Y squared minus X squared. So Y is acting like P, the momentum. So in the lowest Landau level, what happens is that you would have no dynamics unless you have a potential. So now what you're left with is the saddle potential creates the effective potential, right, for this particle to be moving around. But when you look at this non-commuting thing, what you really mapped it onto is a 1D quantum problem where you have P squared minus X squared, minus some constant times X squared. So what you really have is you have a 1D problem where you have an inverted harmonic oscillator. So it's not so much the topology, it's not so much the anyons, though anyons would be a great place to explore this. It's more the non-commutative nature of the lowest Landau level.
So this is like the mapping to inverted oscillator is through this non-commutative nature of this lowest Landau.
Yes.
So I mean, the way I would think is that the inverted harmonic oscillator has all these unstable orbits. So it's the only thing that it can be is classical in some sense, but that's just like semantics, I think. Hello, Smitha. I think you're frozen. Alex, do you hear me?
Yeah, I hear you.
Yeah, okay. So I was just checking if it's not my internet connection.
No, it's probably your commentary.
Let me text her, message her. Yeah, I think we lost the speaker.